Welcome. Let's look at lesson 7-2G, as I'm calling it. This just kind of goes on and on. We're really into these involved integration techniques. And yesterday we looked at the inverse trig ones. They worked out pretty nice, didn't they? You just had to get things situated into a format, recognize the format. For instance, on this one here, I would have said, oh, it's going to be an inverse trig because I've got an u squared plus an a squared, and you could recognize them quite nicely. Today, you're going to think, oh, this looks like what? U squared minus a squared, and think square root over it, that could be a secant inverse. However, what we're missing is that u out front to make it officially secant inverse. So what's a person to do to solve this integral? Well, there are techniques to do it, and we're going to utilize those Pythagorean theorem identities like 1 minus sine squared equals cosine squared and so on. So we will make use of that. It's going to be fun. All right. When I look at this one, I would love to, so I have like u squared minus a squared in my mind. And that kind of flows with this secant squared minus 1, doesn't it? So I think what I'm going to do is set up a substitution where I can put in that secant into this. So let's let, what I got to do is get 36 to just a 1, right? I need a 1 on this. So in order to do that, I am going to go 1 over square root, and I'm going to make this x squared minus 36, but then I'm going to modify this in front and go, oops, that's fat ink, 36 over 36. Sorry, that didn't hold. I said it at the beginning, but it didn't take. Why would I do that? Because then I can go 1 over, and I can factor out a common 36 between the x squared. Now I'll still have x squared over 36 minus 1. If you look at the distributive step, it would get us back to where we started. Now, oh, little dx in there. Let's call this dx up there. Next step, I'm going to take the 36 and square root it and bring it all the way out front. So I get 1/6 the integral, because right, this would have come out as a 6, and now I'm just pushing it out in front of the integral. 1 over x squared minus 36, take away 1, big square root dx. So if I so this is like secant squared minus 1. For our substitution, and maybe you want to even use a different colored pen, let's let x squared over 36 equal secant squared x, because then that's going to achieve a secant squared minus 1 under the radical. Now square root both sides, and we get x over 36 equals secant. Ooh, I don't want to use x. There's a mistake right there. Go with theta, because I can't use a variable that's already been taken like x. So let's go secant theta, and now take the derivative, and we would have, oops, I didn't take square root of 36. Now we'll have 1/6 dx equals, what's the derivative of secant theta? It's secant theta tan theta d theta. And you're wondering, how is she doing this, or why are we doing all this? Well, keep that off to the side, okay? Now, let's go back over to our integral and make these substitutions. It's going to be like magic the way this works out. So, x squared over 36 is the same thing as our secant squared, isn't it? So I'm going to go secant squared theta minus 1. And dx, what does dx trade out for? Ooh, I'd have to multiply by a 6, wouldn't I? So I'm going to multiply by 6, and and do my substitution for dx. So I'm going to end up with 6 secant theta tan theta d theta. Got it? Now you can see that the 6 over the 1/6 will multiply to give us 1. What is the square root of secant squared minus 1? Well, secant squared minus 1, I'm going to go ahead and write the secant theta tan theta d theta on top over square root. Secant squared theta minus 1 is a tan squared. So replacing that from prior step into a tan squared theta, now we can take the square root of tan squared theta and it becomes just tan. See a tan on top? Yeah. Okay, so tan theta cancels tan theta, and I'm left with a secant theta d theta. That's crazy, right? It came down so nice. Now we know the integral of secant theta, or if we don't, we should memorize it. It is on our gold sheet. It becomes a natural log of absolute value secant theta plus tan theta plus constant. Okay, that's an answer. But notice how our answer has a format of, I want to get to the highlighters, what I'm trying to do. Well, this is pretty bright. Of thetas involved. Well, we should have x's involved. Now, there's another step to make that happen. So this step is going to be all about get back 2 x's. Hopefully that'll make sense in your notes. So here's the steps we have to do that. I need to know what secant theta is. Ooh, I know what secant theta is. Secant theta is x over 6. So I've got one little piece. I've got natural log of x over 6 plus, now I don't know what tangent is, do I? But I can figure it out because from this, I can write a triangle. And maybe you remember doing this in pre-calc. I'm going to make a right triangle. I'm going to call this bottom my theta. Secant is really the same as what? Secant corresponds with 1 over cosine. So this really is, well, let's just write 1 over cosine so we remember. And 1 over cosine or secant would be hypotenuse over adjacent. So let's pop in our hypotenuse corresponds to the x, and our adjacent corresponds to a 6. That's the adjacent side. Now can you figure out tan? Well, tan is opposite over adjacent. So it looks like I need opposite. Pythagorean theorem comes into play. So I could figure out this side by going, it's the square root of, well, it would be, I'm trying to decide what to call that. I'm going to call it b. B squared plus 6 squared equals x squared. Solving for b, I would get x squared minus 36, and then I'd have to square root because I needed to get from b squared down to b. Oh, so this side is x squared minus 36. Now I can write my tangent by looking at my diagram here, my triangle. Tangent, opposite over adjacent. So it will be a square root of x squared minus 36 over 6 plus some constant. Wish I had a little bit bigger screen so I could write a little more clearly on here. But that is solved. And, you can just see the complexity in it. Nice problem. All right, let's go on and do another. Oh, there was one trick on this one. I should finish this up. All right, the trick is, the trick is this can be simplified into a better answer. So they both have 6 as their denominator. That means I could write this as x plus square root x squared minus 36 over our common 6 up above, common denominator, plus some constant. Get rid of some of this. Now, one more little trick. There is a rule for natural logs that says the quotient of things, or the quotient turns into subtraction. So I can make this x plus square root x squared minus 36, absolute valued, minus natural log of 6. I don't need an absolute value on it because it's positive anyway, plus c. Do you recognize that natural log 6 is really just a constant? It is, isn't it? Which allows us to pull these two together and really bring this down to natural log of x plus x squared minus 36 with a radical over that plus a new constant. I can call it c sub 1 if you want, just so you can see it changed from prior step. That is really the final answer. Promise. Okay. Oops, what happened to my b? It's right there. I feel like I must be on. That's homework. Okay. Yes, I do have 2 to a page. Typically, I make them each individual. I'm going to erase the top part, and then we're going to roll with this bottom part. All right. So looking at b here. Oh, it's not even in the denominator, is it? But when I look at this pattern, 1 minus x squared, that kind of reminds me of a 1 minus sine squared. And if I could get cosine squared underneath the radical, then I could take the square root of cosine squared and get cosine. I'll also have to be substituting out, the x to the 4th. So I really feel like this is our substitution pattern that we're going to want to go after. And it looks like it might be pretty straightforward for us. So last time we had to do, pulled out that 36. This time we have just like an a squared minus u squared idea, so it'll be easier. Let's let x squared be sine squared of theta. Now we're going to take the square root, so we can just talk about x, which will allow us to do some, shifting there too. X equals sine of theta. Next, derivative. So the left side would really be a dx d theta. I didn't say that last time, but that is what happens there. And on the right side, the derivative sign will be cosine theta d theta, which I don't need to write. But then I can modify left side over to right side here by multiplying up by d theta, so that we have all of our necessary substitutions ready and available. All right, now let's do the work. So we said we're going to replace x squared with sine squared theta. X to the 4th would be a sine to the 4th, wouldn't it? Dx changes out for a cosine theta d theta. Just be very intentional about what you substitute. Every single thing needs to be accounted for. Now, next step, let's simplify that radical. 1 minus sine squared says it's equal to cosine squared theta over a sine to the 4th theta. And then we get a times a cosine theta d theta. Well, the square root of cosine squared will be just cosine, won't it? And, oops, cosine theta times cosine theta. We could have written a cosine squared theta, but I just didn't for you to be able to track our steps. Now we definitely are in a cosine squared theta over a sine to the fourth theta, didn't need that quite so long, d theta. Some of that trig substitution that we did earlier kind of comes to mind for me. And what would I want? If I would have had just a cosine, that would have been fabulous, because then I could have let u equal sine, and its derivative would be cosine theta d theta. But we got a cosine squared. Let's try breaking this into, I'm thinking about going squared squared on the bottom. Why would I do that? Well, I could call this now, that's a cotan, isn't it? That's a cotan squared theta times a cosecant squared theta d theta. And think back to your u substitutions when we did trig subs. And if we let u equal cotan, its derivative is cosecant, isn't it? All right, so a little u substitution here. Wow, huh? Gotta love these. All right, let's let u equal cotan of theta. Du equals cosecant squared theta d theta, but I believe it's negative. So that'll be an adjustment of a negative du equaling a positive cosecant squared d theta. Okay, back over, and let's substitute out. Cotan squared is our u. That'll be a u squared. Cosecant d theta is a negative du. Oh, this looks simple now, doesn't it? Negative 1/3 u cubed plus c. Sub it back, and we will have, I'm going to triangle horizontal here, negative 1/3 u was cotan theta. That looks like that'll all be to the third power, won't it? Plus c. But that's not yet our answer, because I have theta and I started with x's. So we have one more substitution to make. Would we get lucky and know what cotan was? Not off of this, right? Not off of our original setup. So let's go to the triangle work and triangle work. Where is our theta? Well, to pick one of the acute angles, I'm going to make it down there. And what do I have to work off of? I know that sine is equal to x. That's like an x over 1, isn't it? And sine is opposite over hypotenuse. So this is all going to be built off the fact that we have sine theta equals x over 1, opposite over hypotenuse. And then this would become hypotenuse squared minus leg squared equals the other leg squared, so I square rooted it. That's all Pythagorean theorem work. If you are still questioning what I did there, just let this, I'm going to let this be a squared, and then solve it out. So 1 minus x squared equals a squared, or a is equal to square root 1 minus x squared. Okay, now that we have our triangle, we should be able to figure out cotan. I know that cotan of theta would be, well, tangent is opposite over adjacent, so this must be adjacent over opposite. Adjacent is the square root. So back to our answer, we're going to have negative 1/3 cotan is going to be adjacent, which is our square root stuff. Opposite is x. So it's going to be square root of 1 minus x squared over x plus some constant. And let's just leave it, that's fine. Beautiful. Next, these get fun. They're kind of fun, but they are involved, that's for sure. Next one, I have 1 minus e to the 2x. Just to recall, e to the 2x could also be written as e to the x squared, couldn't it? Because power to the power means I multiply. So keep that in your mind. And I'm kind of seeing 1 minus sine squared. I'm picking this as my conversion, my substitution technique here. I would love to get a cosine squared written underneath here, because then I can take the square root and get a cosine. Let's try it. Oops, that's weird. All right, let's try. So we said we're going to let our u squared, no, what's with u squared? That's not the right start. E to the x quantity squared is going to be set up as a sine squared x. I have the 1 over on the original problem, so I just need to make this my e to the 2x. Now take the square root. We got e to the x equals sine. And here I go with x's. That should be theta and theta. Oh, goodness. I just noticed these should all be theta, shouldn't they? No wonder why I keep writing down wrong stuff. All right, now derivative. E to the x dx equals cosine theta. This would have been d theta, right? Move it up and over, and we're over there. Implicit differentiation. All right. Ooh, that's convenient, because look at e to the x dx. That's going to be a nice substitution. All right, let's go about our substitutions. The square root of 1 minus, we said let e to the 2x equal sine squared theta. And ex dx, those come together to create cosine theta d theta. Now, 1 minus sine squared is cosine squared. And we have a cosine theta outside it. That makes this cosine theta times cosine theta d theta. Or we get a cosine squared theta d theta. Oh, good thing we studied how to integrate evens. With integrating evens, we use that power reducing formula, which will give us 1/2 integral 1 plus cosine, double the angle, d theta. I pulled my half out front. That I can integrate, can't I? That has a nice integral. The integral is, the integral of 1 converts to just theta, and the integral of cosine converts to sine 2 theta. But because of 2 giving a chain rule of 2, I need to offset it with a 1/2 plus some c. Very good. Now, let's take our half through. We have 1/2 theta plus 1/2 sine 2 theta plus c. Okay, the theta I think I can handle, but I'm wondering about this double angle business. What are we going to do with that? All right, so theta, from this we can solve for theta. And that would look like we'd have to sine inverse both sides, wouldn't we? So sine inverse of e to the x equals theta. Beautiful. Now, what about the 2 theta business? Okay, so we got 1/2 sine inverse of e to the x. Oops, not e times x. Plus 1/2 sine 2 theta. Well, there is a story for this, and the story goes that, oh, this should have been, we distributed, this should have been a 1/4. Sorry, make that a 1/4. Um, Sine 2 theta. Back in pre-calculus, you had a formula that said sine 2 theta is equivalent to a 2 times sine theta cosine theta. See, eventually you knew these trig identities would come in handy, and who thought it would be at, oh, I gotta erase here, at Calc 2 time, huh? Okay, so we have that 1/4. Instead of sine 2 theta, let's get this down to just a single angle of theta instead of 2 theta. So it's sine 2 sine theta cosine theta plus constant. Now I need to know what sine theta is, and I think I might have that. Sine theta is ex, e to the x, but I don't have cosine. Guess what? We get to make a triangle. Okay, so we're going to build a triangle off that. The triangle, let's put the triangle in green. Here's our theta, and we knew sine was opposite over hypotenuse, and this would make this 1 squared minus e to the x squared, so e to the 2x. I don't know about you, but I've noticed that often this, where we started with our integral, is often the missing piece to our triangle. So now, full substitution, last step. 1/2 sine inverse e to the x plus 1/2, because 2/4. Sine of theta we said was e to the x, right? Yes, e to the x. Cosine of theta is adjacent over hypotenuse. So adjacent would be square root 1 minus e to the 2x over hypotenuse of 1, so no reason to write that down. And there's our answer, as lovely as it is. I mean, these are just amazing how they work out. Never would have ever guessed that as an integral for this, correct? I mean, we look at our gold sheet, and those seem so simple now compared to what we're working with here. And we used many techniques. We had to know the double angle down to single angle formula for sine. We had to know our trigonometry setup for triangles. We had to know our Pythagorean identities for trig, so that we could do the original substitution. Yeah, just so much going on. All right, this looks good. So on this one, well, it looks like 1 minus e squared x, doesn't it? Or e to the x squared, which is very similar to what we just did. But there is one very sharp difference. It's e to the x versus e to the 2x. You will be relieved to know this is back to our good old u substitution. We could let u equal 1 minus e to the 2x. Take its derivative, and we'll have negative e to the 2x. Chain rule brings it 2. We don't need two of them, so we have a negative 1/2 du equals e to the 2x dx. Oops, missed that dx on that prior line. Everything should flow smoothly. This particular problem is sitting in here so that you just don't always assume, that they're going to stay that one type. We will have to, that's going to be the challenging part, is looking at any integral and deciding what technique to use, because you have way more techniques than what you had in AB, that it will be a deciding factor of what to use. Much like taking derivatives. Do I use chain rule? Do I use product rule? Quotient rule? You all had to analyze your problem and decide what to apply. So same will go here. Let's do our subbing out, and I think we'll be home free. So negative 1/2 e to the 2x dx is a negative 1/2 du. This all gets put as a u to the 1/2. Okay, easy peasy. Add a power, divide by the power, or multiply by the reciprocal, plus c. 2's are going to cancel. We're going to get a negative 1/3. Replacing u with 1 minus e to the 2x gets raised to the 3/2 plus c. Oh, don't those seem easy now compared to what we've been through? Your homework, you can tell that there's plenty of work. 5 problems will be adequate. I gave you the answers so that you can hopefully make use of that. So analyze them first because maybe you don't need to use the big trigonometric substitution. You might be able to do U sub. Look at here, it says U sub may work on a couple problems. That would be nice, wouldn't it? All right, have a good day.